but here it does make a sense, So if you are here, the big picture was, I want to really understand with confidence that manipulating phosphorylation status does something, right? And pushing it down and pushing it up as a complete experiment makes sense to me. I mean, to keep it together. So that if you get a consistent pattern with that.
Although there could be a biological explanation.
Correct.
Right?
Exactly.
The optimum level of phosphorylation is something.
Exactly. That's exactly what I mean by your biological understanding. So here we just a priori assume that putting it up and putting it down may have symmetrical and opposite effects, and we are losing out on that. What happens if there is a saturation? It's not symmetrical, or it is something. It's not symmetrical. So then your stats will just go away. Sometimes it'll not come out right. Then you make those arguments or analysis based on that additional thought process that you might have. So really, statistics doesn't help you. But this often happens. But it would be equally wrong that just because we lost some of this, we just completely forget about it, never say we did any experiments, and just report this. It may be wrong also, right?
In this case at least, you did something on the same site, involving the same site.
Yeah, that's why. We expect that it should be a stronger...
But so then I see it's somewhat ethically incorrect to completely ignore it.
Yeah. So we can't...
What if you were doing something independent? That's a signaling, 3 different signaling pathway blockers.
Yeah.
So one day you did a signaling pathway 1 and you saw a difference. The next day you did an experiment with 3 7.
Yeah. So there I think there is no reason to sort of, even though you want to, let's say, for some, there must be a reason why you're reporting all 3 in one paper, correct? Is that?
Well, then you decide later. You decide, no, I don't want to report the other 2. I just.
That's okay with me. I mean, this is exactly what I mean by what your understanding.
Is it ethically incorrect?
No, I think it's completely up to you. You'll have and statistics is not going to help you with any make decisions as to ethical or not ethical. That has to come from something else. Your understanding, your rationale. Really, that's where the issue is. So this is one example which is troubling right now. So anyway, once you have the analysis of variance tell you that we are rejecting the null hypothesis, all it is saying at that point is that there is a difference somewhere. And so oftentimes you have to do multiple comparisons post hoc. So you guys use multiple comparisons afterwards. So what's the test of choice for you guys? Tricky. So okay. So there are many of them, and all I wanted to do is, of course, I'm not going to tell you an exhaustive list and give you a prescription, but just again, concept. What makes this test different? What is the basic difference between them? All it is how ultimately it boils down to the following: how conservative you want to be, and how liberal you want to be. What does it mean, conservative and liberal? Conservative simply means that you are averse. You just don't want to make mistake in saying that there is a difference. You really, really, really want to be sure that when you say there is a difference, there is a difference. That's conservative. Liberal is you're quick to say there is a difference. That's basically liberal. So the tests that I'm going to show 4 or 5 tests, they differ in their approach. Now again, at the end of the day, you end up saying, so which one should I use? It's a choice you make, and I have personal choice, and I would say. So what is the key point? So that Partha said, then I had four groups. Let's say I'm just taking 4 groups as an example. So I had X1 bar. And I did an F test, and I got significance such that the p-value for that F was less than 0.05. Okay. But everybody sort of knows what that p-value means, right? 0.05. That means there is only a 5% chance. There's only 5% chance of you conclude that you may be wrong. Wrong in the sense you are concluding that there is a difference. So that conclusion of having a difference is in fact not the real answer is there's no difference. So there's only 5% chance of that. So that's a p-value. Sometimes called type 1 error. So it's a probability of making an error. But what kind of error? Concluding that there is a difference when in fact there is none. That's the error. Null hypothesis is correct. So concluding and rejecting the null hypothesis. There is a reverse part of it, which is type 2 error, which is just the reverse of it. Failing to observe a difference when in fact there is a difference. And that's more related to power of the test. So oftentimes when you get a low p-value is not high, that means it's not below 0.05, that means you didn't observe any difference. People then question, did your test have enough power to guard against the second kind of error? So you didn't find a difference, but what is the probability? There, the relevant question to ask in terms of error is what's the probability of saying that no difference, when in fact there's a difference, and that's related to power, and that relates to you have enough experiments and those kinds of things. That's the second type of error. Anyway, so this F was, let's say, fine. So then now we want to know where the difference resides. Where is the difference? So one exhaustive way of doing it is all pairwise comparisons. X1 with X2, group 3, 4. Then X2, group 3, 4. Then X3, 4. So we have 1, 2, 3, 4, 5, 6. 6 possible comparisons you can make. Exhaust, mathematically speaking. Sometimes the structure, the experimental structure is such that some comparisons don't make any sense, biological sense. You don't want to make them. So you can remove those from your comparisons. So first immediate idea comes to mind is that why can't I just take this and do a straightforward t-test? And then just keep doing t-tests. So it will in this case it will be group 1 versus 3, group 1 versus 4, 2 versus 3, 2 versus 4, and 3 versus 4. Why don't I just keep doing the t-test and report that? And so the key answer there is guarding against this. So if you have, so in this case 6 tests, right? Each one is being tested completely with blind eye towards the other data. Each one you're willing to accept 5% error. That's your thing. So if you're doing this 6 times, these 6 comparisons as a whole will have about 30% of finding a difference when there is none. Somewhere. So your overall P is not really 5%, but 30%. Effective. And that's the problem. So basically you just sort of keep trying to find something and you just by chance will find. Just one. You just need one difference and that's it. But you have now 5 different chances to find them, and each one having 5% possibility of an error. So it's 30. So that's what you need to sort of guard against. And so therefore you do this first test. Here everything is being considered all together, and it gives you. So there is a difference. Then we are now on solid grounds. Like there is some difference, and go ahead and find that. So the many options. That's what I said. Conservative. The most common and most sort of the easiest to do is bound ferocity test. So basically, you just do exactly what you're doing here, but instead of checking. So let's say we were going to do all 6 comparisons for these 4 groups. This exhaustive combination of all. biologically, that's what we want to do, right? And as I said, if we do it each test at 0.05, overall error is 30%, right? So what you just do reverse, don't do it each 0.05, but you do 0.05 divided by 6. So you will accept the difference in each one and make the criterion stringent. So it's, that will be 0.001, 009. So each one has to satisfy that, so overall remains within 5%. That's the easiest way of doing it, you know. But you can see how conservative this is going to be. It really requires a difference to exist somewhere. But that's a bond for it. So basically, you just change your critical value to 0.05 divided by the number of comparisons you have chosen to make. As I said, there's no need, even there are 4 groups. Maybe this was a wild-type animal, this is 3 mutations, and biologically the only thing you're interested in is this mutation change with respect to control. Maybe that's the only relevant thing to you. So, put only 3 pairwise comparisons. So if you don't do any more comparisons, I mean, you upfront say that's all 3 you want to do, your division by k here will be just 3, even though mathematically 6 are possible. So that's okay. And that's, but nevertheless, this is sort of.
So when you report it, you wouldn't call it a Bond-Ferroni test.
Yeah.
So we did a
Bond-Ferroni test with the multiple comparison restricted to these 3 groups.
Okay.
Up front, that's the. Now, you can come back to say to me that, did they really think of that, or they just made that up after the fact, How can you never get find out, Whatever it is, but as long as it makes sense. But biologically, sometimes it does make sense, why would you compare one versus another? Another good example was, we had something where it really didn't make, mathematically, you can list, but this 2 versus 4 had no reason to compare. You come to some example. You just immediately see physically doesn't make sense to compare them anyway. Okay. Then another one, Holmes test, is similar to Bond-Ferroni, but it adjusts the critical value after each comparison. So what I'm trying to say is that if you do one, let's just in this example. So here in this example, Bond-Ferroni, if there were 6 to be made, your critical value is whatever t.05 divided by 6. It's a constant for all these comparisons. What this other test does is that you first find p-value for uncorrected p-values for all of them, just like regular t-test, right? And then you start with the smallest p-value. So you organize them. So there will be 5 p-values for 5 tests, and you rank order them. This is the smallest. This is the largest. Smallest means that has the most significance. So now, for this one, the k would be 6. The k is the division factor in that Bond-Ferroni, so it's 6. And then it reached significance and it did done. Now if you're doing this, it will be then 5 here. Because already we found a difference there, that's fine. So now this is 5. Instead of Bond-Ferroni, we'll keep 6 for everybody. Everybody has to meet that stringent criteria. So t has to be 0.05 divided by 6 for all of them. But here it will keep going down. And if you keep finding difference, the last one will be just 1, standard t-test. So that's the only difference there, So this it's a little less conservative. That's it.